Hi, Sterling Allen here, PESN. I just got back from the Solar Hydrogen Trends demonstration of their Symphony 7 hydrogen producer that was tested in January by Air Kinetics Inc., which specializes in those kinds of measurements. And their numbers showed an overunity in one of the data sets of 577 times. So for, I think it was close to 700 watt input, they were getting 577 times that much energy out in the form of hydrogen, which has a kilowatt equivalent. And so that was a rate of about, what they supposedly measured, or what they reported in their data, was something along the lines of 2,300 liters a minute of gas coming out. And what I saw was obviously hydrogen gas production, but it didn't seem to connect to me that it was producing that much gas. And I ran some numbers. They had an anemometer that a 1-inch diameter opening with the handle, and you put the 1-inch opening. They had a 1-inch, maybe 1 1/4 inch size pipe coming from the tank that was making the hydrogen gas. And as he placed the anemometer on top of it, it wouldn't turn. And it has like a 186 cubic feet per minute lower end limit on the anemometer, which I think comes to, what was it, 200 and it's like 3,000 something liters a minute. It's way up there. So it would make sense that wouldn't spin, even if it was producing the amount of gas that they were claiming. I was expecting, just trying to think, what would 1,000 liters a minute look like, or 2,300 liters a minute on their higher setting. And I was kind of picturing that you would have pipes that would be screaming because of the exhaust of the gas. I was wrong in that assumption because, number one, hydrogen gas is 14 times less dense than air. And so when you have air coming from a pipe, you have a certain air volume sound, you have to reduce that by 7 times. And so, if I was doing that with hydrogen, it would sound like, you obviously can't hear that from there with that camera. And so that's one factor. Another factor is that I'm getting ahead of myself. I wanted to mention that when they put the anemometer, they had an opening that was about, I just got a syringe here to approximate the size. This is about 3/8 of an inch, and they had about a 1/2 inch opening when they were taking the hydrogen gas sample off to send to a third-party group for testing, for qualitative analysis of what percentage of hydrogen, oxygen, and other contents of that gas. As you blow through this, that sound actually approximates the 1,000 liters a minute. It's actually 720 liters a minute, because your lungs are about 6 liters. The average male lung is 6 liters. So if you inhale all the way and then blow out as fast as you can, which is about half of a second, just try it, time yourself. I did this on the plane coming back. It takes about a half a second to vacate your lungs. And now with this is going to be restricting the flow, so it's going to be a little bit harder. But here's what it's going to sound like for 1,000 liters a minute. Well, actually 720 liters a minute of gas coming. This is air, not hydrogen gas. And so I'm going to inhale all the way and then blow it out. Part of that noise was coming from the squeaking sound of my lips going around this thing. But let me just do that one more time. I mean, that's you can hear that, and that's fairly loud. The volume on the camera doesn't really do justice to loud or soft decibels because it adjusts for the sound input, so it doesn't overwhelm the audience. But you can do it yourself. Just get something that's about at half-inch in diameter, because they had a half-inch diameter tube. They had an apparatus plumbing to fasten to the outflow of the gas with the. They had a fitting for the tank to take a sampling of the gas. The tank was in a vacuum, so that it wasn't contaminated by previous contents, and it would suck in the contents of the gas. And before they did that, they vacated the top of the, there was maybe 2 to 3 inches at the top of the chamber, which was maybe, this big. And that was their reaction chamber. And then they had a circuitry and whatnot over on the side, and then they had the power supply in front of it. And we've got pictures of all this. But as you're, they had this much gas at the top of the chamber, and so they had a big acetylene type torch that was under vacuum, and they hooked that up to the outflow of the gas and of the tank, and they sucked out, basically put the top of the tank into vacuum, sucking out. There might have been some nitrogen left from the air, some oxygen, and so they wanted to vacate it as much as possible to eliminate any contaminants, put it in the vacuum. So they sucked out the contents from the top, and then they opened the spigot to the collection tube, and it pulled in the gas, and then they closed it. So that's how they took the sample. And so that's why they had this small opening on there during that period of time. And while they had that 1/2 inch opening there, they put the anemometer in front of it, and if you got it just right, it would actually start spinning. And it was right to the point where it's just, it takes energy, like in a wind turbine. You have to have like 7 miles per hour wind for the turbine to even start spinning. So it's not like it starts from 0 miles an hour, and at 1 mile an hour it starts spinning really super slow. It has to get up to a certain critical point to overcome the friction and to get it to start spinning. And so the same thing with this little turbine in the anemometer. It has a certain low end speed that the wind has to be at before it'll even start spinning. And it was right at that point of where it was just starting to spin. As you put the anemometer's an inch in diameter, and the opening was maybe 1/2 inch. And so as you put the 1/2 inch opening in front of the anemometer, the thing would just barely start spinning. So what I did was I took a hose that was it was about a 5/8 inch hose. This is a lot bigger than that. This is, 7/8 or 6/8, 5/8, something in that ball. Yeah, I don't know. Anyway, it was about a 5/8 inch clear plastic hose, and I put that right in front of the anemometer, and I blew. I didn't take a full intake of breath for the full lung capacity, but like you're singing, just before you take a breath before you say a long sentence or something. I just took a breath and then blew at a slow pace to just turn that anemometer at the same rate. So it was just barely turning. Sometimes it would stop, and then I'd blow a little bit harder and it would start turning again. So I just kept it right at that rate. And it took 24 seconds for me to expel all the air in my lungs. And I calculated that was about 12.5 liters a second. But then you have to take into consideration that air is 14 times more dense than the hydrogen. And so you have to multiply that times 14. And so that basically comes to 175 liters a minute. And when you take 175 liters a minute of hydrogen, and you also factor in that it's 93.1% hydrogen according to the air kinetics data from January, that comes to 9.3 times over unity from that data. That's a lot less than the 577 times over unity that air kinetics reported in their data. But I think given the that's still very interesting. It's still a huge breakthrough. And the ratios that they're talking about, which was actually verified by two independent parties, Air Kinetics, and there was another one that they don't want disclosed because the company doesn't want their name out there. It's a big company that, they're very professional and they know how to do these kind of measurements. And they also confirmed the ratio, and you've got water, H2O, in a chamber going out through an exit from this electrolysis plus 16 total processes going on at the same time according to the inventor. You've got cavitation, you've got possibly cold fusion, you've got electrolysis, you've got sound. There are a lot of things going on at the same time to have this massive production of hydrogen. And so it's my understanding, and as I was thinking about, just what is it going to sound like, the opening to the from the tank, they had a PVC fitting that came down to, it could have been an inch, it may have been an inch and a half. This is probably, an inch and a quarter. This is probably an inch and a quarter right here, just a painter roll here. And so what I'm going to do is I'm going to expel full volume in half a second, my 6 liter lung capacity, so you can hear with air, what 1,000 liters per second sounds like, or 720 liters per minute, Okay, here we go. You hear that. And that's kind of what I was expecting to hear and to witness when I was watching this demonstration, if they're getting this much volume. Actually, my expectation was much higher than that. I was thinking it could be, even sounding as loud as a jet engine or, something like that. Just massive volume. As I do the numbers, doing this kind of reality check of what does that sound like. Now let me just, I'm going to turn my timer on here, and I'm going to, I'm going to do this now over 7 seconds. You heard what it sounds like in half a second, which is 720 liters a minute. Now I'm going to do that over 7 seconds, which is going to be the adjustment for what hydrogen would sound like, because it's 14 times less dense than air, and it is it's also, it's a smaller molecule, so it's not going to interact with the surroundings in the same way. And so I'm going to turn my stopwatch on, and I'm going to vacate my lungs roughly over 7 seconds so you can hear what it sounds like, the difference, okay? Okay, that was 8 seconds. I'm going to pause for a second and do that again. Okay, so that's what the difference in the volume sounds between hydrogen and air. And so there's, it's obviously a huge difference. And also, let me do the same thing with this, this small opening here. Reset, okay. Okay, I'm going to do that again because I wasn't even close. I needed to go faster than that. Because this is more restricted so that the lungs are not wanting to expel it as fast. So, ready? Okay, that was 8 seconds. So I could hear that still. I could hear that as the molecules were hitting the side of the chamber, it was still resonating and vibrating this little tube. And I cut the top of the syringe off, by the way, so you know that it's not, you won't have that small restriction at the end. So you can still hear that, and that again is the equivalent of 720 liters per minute of hydrogen. It's audible, you can hear it. When I put, and also I would argue that from just my experience with the anemometer, we were blowing on it, you put a foot away and it just, put a little breeze on it and it would start spinning from this far away. You take it in the air and move it and it would start spinning. So, if you have that much airflow coming out of a 1-inch tube from a gas that's being produced that, comes to, that many 168 minimum cubic feet per minute. But anyway, the reason we're having to go through this whole rigmarole with the anemometer and all this stuff, we had everything we needed on hand there to do a really accurate gas flow measurement. And the inventor considers this barbaric measurement technology because it's using stuff you can get from around the house. We had about 5 gallon buckets sitting there. They had a swimming pool where the demonstration was. We were out there on the swimming pool deck. And there were 4 buckets they used to fill the chamber. They had a 2-liter bottle. This is not a 2-liter bottle. I don't think. It's 3 quarts. So it's, US. But, this is the approximate size. And it has a little smaller opening 2-liter bottles do. But the idea is you just take, if you fill it up with water, you've got your 5-gallon bucket, almost full, and you push this down into the water, you fill it up with water, you screw the cap on, you turn it upside down, so it's full of water, completely full of water, you set it down inside the water, you take the cap off, and you all know from playing with as a kid that if you take the cap off while it's underwater, it will stay full of water. It doesn't evacuate until you let some airflow in. Then the air comes in and it the water drops down. So you keep the opening of the bottle underwater, and then you take your hose, and they had a hose attachment for the outflowing gas. You take the hose and you run it into the bottle under the water, and so now the gas is flowing into this bottle, and it starts, the gas bubbles cause the water to drop down as it fills up. And you calibrate this, you put a mark on here, you take a graduated cylinder, you take 2 liters, you mark 2 liters on here, and so you know that when the gas gets to that level, and when it comes down, that's 2 liters. And you also hold up the bottle so that the water level in here is matching the water level at the top of the bucket. And so there's no pressure difference between the bottle and the water bucket. And so basically what you have is 2 liters of gas by any definition. We were at sea level nominally in Pasadena, California, maybe 100 feet above sea level. And barometric pressure, but we were nominally close to all the atmospheric conditions to make for a very, very accurate 2 liters per however long it takes to fill that up. And it would have been just a few seconds at 1,000 liters a minute. That's what is that per second? I can't remember. It's anyway, it would fill this up in a few seconds, and you would be able to have a reality check that. In fact, I would argue that this measurement technique, as barbaric as it is, because anyone in their household just about has these items that you can measure with, but it's to use a crude analogy. Some things are just timeless and they work. you get a male and female together and they have sex and they have babies. I mean, this is a law of nature. And by definition, this is 2 liters of any kind of gas is going to fill this chamber, 2 liters. And if you have that water level the same as the water level in the bath, there's no pressure in there. You've got a 2.0 liters of water to an accuracy of probably 0.1%. And so this is a very accurate measurement. My dad, an atomic clock physicist, agrees that this is very accurate. The air kinetics guy that we had there with us on Friday, he agrees that this is very accurate. The guys from the U.S. government that were there to do the testing, the main reason for the demonstration, they agree that this is very accurate. But the inventor, he was just, for some reason, he just did not want to be associated with, taking a measurement by such primitive means, so to speak. As accurate as they are, I guess just the association of, measuring it with a bottle, I think he was in a disconnect, and he was in a state of denial, not wanting to, have this reality check of what his thing's actually doing. So that's why we were doing all this stuff with the anemometer. We had this thing that they did have that they were testing, which was, in my opinion, much, much, much less accurate than this method. This method is going to be plus or minus 0.1%, 1 to 0.1%. It's going to be in that region, very accurate. Plenty accurate to confirm 577 times over unity. Plus or minus 1% is, 560%. I mean, that's the level of accuracy. That's plenty good to show the world that this really does what they claim it does. Whereas with this anemometer, you're probably plus or minus 50% in your accuracy. And if you look at the data that Air Kinetics collected, they had the first 2 runs were both about 400 watts. It was, that you take the volts and the amps, and they were very close. There was about 3% difference between the watts going in through the power supply to the device, 3% difference. And yet the gas flow that they measured was 33% different between the two, test 1 and test 2. And to me, that shows that their accuracy is at least plus or minus 33%. The reproducibility, if their data is actually that accurate, that shows that the device is all over the place and it's not stable, that it's unpredictable, that it's you don't have an even flow of gas. But I doubt that that's the case. I bet the gas is very constant, that it's very even, that it's it's not jumping all over the place. And what is moving all over the place is their measurement apparatus. They had a 8-inch tube. This is how they measured their gas flow. They had an 8-inch PVC pipe, approximately 8 inches. It's about a foot and a half long, with maybe a 3-inch opening that they used to screw on the top of this apparatus of their tank. And so they had this pipe, an 8-inch pipe, with 2 little instruments in it to measure the gas flow rate as it was going by. I'm sorry, but you just get a little breeze going by there, and that's going to be stirring that thing up, even just the ambient air currents and whatnot, and the turbulence. There's no way that's nearly as accurate as this right here. Absolutely no way. And their data shows that they're all over the map. 2 consecutive runs, they did 3 total, with a 33% difference in the number on the outflow of the gas. And I think that both the variation and the amount was way off. That they were measuring 82 cubic feet per minute at the highest, and they were measuring about 32 cubic feet per minute at the lowest. And we were probably, according to just this rough estimate using the anemometer, almost 100 times lower than that. it's still over unity. It's still very significant. 9.3 times over unity is a rough estimate using the anemometer and blowing into it, with my breath to approximate the same speed, and then multiply by 14 to convert to the hydrogen gas. It would have been so much easier to just take that outflowing gas and the tube that they had that had a 1/2 inch opening in it into the bottom of the tube. The water is able to flow out just easily. The gas flows in just fine. There's no impedance. There's no pressure difference. You've got 2 liters of gas, 2.00 liters of gas. As you come to the line, you time T equals 0, T equals 1. You subtract them, you've got liters per minute. That is as accurate as you can get, almost. It's not practical. It's not easy to do this. I mean, if you can get instrumentation, so you just push a button, you get a measurement, that's much more user-friendly. But in terms of accuracy, this is extremely accurate. And, if you want to be even more accurate, then you take into account the temperature and the barometric pressure and all that kind of stuff that you have to do to calibrate for the expansions of the gases at different temperatures and pressures. But still, this is going to be a very, very good estimate of what is happening. Not even estimate, a measurement of the gas flow from that. And so at the end of this, and I think the reality check of blowing in here, and you can hear what that sounds like, that even at blowing at 1/14 the rate to approximate the hydrogen flow through this, you can still hear that. I can hear that. I don't know if the camera's picking that up, but it's just buzz, buzz. It's that tone. Let me just turn the camera really quick and show you what that sounds like. See, you can hear that. And that's what we should have heard if it was, that was 720 liters a minute. And he was thinking that we're getting at least 1,000 liters a minute in that setting because of the data that they got from Air Kinetics. Air Kinetics Inc. I mean, you would think if anyone could measure something like this accurately, it would be Air Kinetics Inc. But I call bogus on Air Kinetics Inc.'s data. And I think that this is going to be much more accurate. The anemometer data that we took is going to be, closer to the approximation. It's still over unity. It's still breakthrough science. It's still very significant, especially the data that you're getting. I started to say this earlier and then I got sidetracked. You've got H2O going to hydrogen gas. Almost 93.1% was the average of the 3 tests that Air Kinetics did. And their margin of error between the 3 tests, it was like 10 points, 10 percentage points between the high and the low. I think their high was like 96 and the low was 86, point something, and the decimal point was the same between those two. So it was a 10.0 percentage point difference between their high and their low. And I didn't look carefully at the other third-party test data and what they measured, but I'm under the understanding that they showed the same thing, that you have this almost pure hydrogen coming out from this tank, this closed tank system, where you've got H2O on the input, which, according to science, you've got oxygen in there, and your ratio on the output should be 33% oxygen, 66% hydrogen, 0.666, etc. And you may have some contamination of nitrogen at the top of the sampling. You're not going to be able to get rid of, even as much as you try and vacate the thing. But that's nominally, and they say that the inventor says that if you were under a complete vacuum, that there would be no nitrogen, and that there would be it would be pure hydrogen with 0 oxygen as well, because you've got some oxygen contamination in air as well. And so that 2.75% oxygen that was the average of the 3 tests could have been just the contamination of the oxygen in the air at the top of the tank from the beginning of the test. And so if you got H2O going to H, that means oxygen is being transmuted into hydrogen, which is huge science. I mean, you scientists out there should be all over this. You should be saying, we've got to study this, we've got to learn about this. There's an effector that's very significant, especially since you're getting a third-party test results that, 577 times more energy out than in. That should get you interested too. I mean, for heck's sake, there's something going on here, need to be explored. So I am calling bogus on the results that Air Kinetics got in terms of the volume flow. I'm guessing that their percentages of the gas ratios is fairly accurate, plus or minus maybe 10 or less percent. But what they wanted to do is I kind of actually went in, not kind of, it went into a wager with the inventor, Constantine, and I said, we came up with these numbers. I said, we'll do a repeat test. We'll have a third-party company that is reputable, that has all the equipment needed to do a professional test using a protocol that we both agree is going to be accurate. And they'll come and they'll do the test, and we'll show, and if that test is more than 1,300 liters a minute with an input of 510 watts. So their power supply is 510 watts, and the output is at least 1,300 liters a minute. What was the number? The Overunity on that? It was like 75 times Overunity, not nearly the 577 that we were talking about with that one data point from Air Kinetics. But that was our wager. If it was more than that much or more, then he would pay for my trip out there to witness this and for the third-party testing. If it was less than that, then I would pay for the test and for my trip to come see this thing, and we would basically have the money on the table, and whoever won that bet would get the money, or the person who lost the bet would pay. And you all know that, or most of you who watch this regularly know that, PES network, we're not rolling in money, and we don't have that kind of money to throw around to pay for a test like this. But the reason I'm confident in making such a wager is because if he really does have 1,300 liters a minute, it's not going to be hard to get people getting all excited to, help cover that expense, and we'll be able to pay that money for him gladly. It'd be like, it'd be a pittance compared to what the technology is worth. This is $1 trillion technology. It's number one. Even at this low number of 9.3 times Overunity, it still keeps it in the number one position in our top 5 listing. Where they're still improving the technology. They've got Symphony 9A in the hopper that they say will be even better. I don't know if they've got it built, but they say it'll be better. Sorry about the interruption there. I'm just expecting a call from Jack. I got the story up, got the video up, and he was taking a look at the video, and he probably has some feedback on that. And they liked the write-up. They thought it was fair. They thought it was very objective. It was what I saw and what I experienced. Like a true reporter, they said you just stated what happened, and so they didn't have any problems with it. Even if it's just 9.3 times Overunity or in that ballpark, it's still breakthrough science. It's Overunity. It's new science. There's something else going on here that can be optimized, characterized first, optimized, and get the math around it, get the science around it, and roll this thing out to the planet. We can use water to power our planet, and the inventor thinks that the oxygen is not being removed from the environment, that you have the oxygen that goes to hydrogen in the reaction, but that on the tail end, in the burning of the fuel, that you end up with oxygen again. But I would argue that that's not the case, because the oxygen that's showing up to match with the hydrogen in any burning that's going on in the combustion of the fuel, unless you're, whatever fuel process you're using to turn that back into usable energy, that's pulling that from the environment. So you're ending up with a net loss of oxygen. And so I think that if this science is real and it's actually removing oxygen from the planet, on a net level, we'll need to have another technology that will replenish that oxygen. Otherwise, this is not a technology that's going to be feasible. So that's going to be one of the early questions we need to ask, is what is the net analysis of the life cycle process from the creation of the gas to the burning of the gas? Do you end up, if you have 5 liters of water, do you end up with 5 liters of water in the end? And the inventor says yes, you're not losing any oxygen in the process. I would be surprised if that's the case. I think that you're losing oxygen. The oxygen is being transmuted. It's no longer an oxygen molecule. I mean, an oxygen atom. It's turning into hydrogen, a different atom. You're changing oxygen into hydrogen, so it's no longer, it's like, there, I won't go there. But it's a transmutation. I was going to use a sex change analogy. I mean, a person has a transgender sex change, and you've got some, they have chemical stuff, hormones, therapy, they do physical surgery to change. You're no longer a male, now you're a female according to your makeup. And you're taking oxygen and you're turning it into hydrogen. It's no longer oxygen. And you're taking, eight protons and neutrons into one, the proton hydrogen. And, you're there goes the oxygen. And if everyone on the planet is burning this stuff, that's not going to last very long. And so we'll need to find another technology that can replace the oxygen if this thing is a genuine, that is actually removing oxygen. And also, they claim that the process, that this is just one of the applications, that you can actually do transmutation of a lot of different elements. You can create a lot of different things on the periodic chart using this device, because they're actually controlling the elemental particle level, what's going on. And so it's very exciting science. I know mainstream science is in a habit of ignoring PESN, but you're not going to be able to do so much longer, because there's some pretty good data supporting a lot of these technologies that we've been tracking for years, and we are going to be vindicated. There are exotic. Science has not figured out everything is to figure out. There are new ways of harnessing the will work of nature. And every time you have a breakthrough, it's indistinguishable from magic, because you don't understand it. But once you understand it, then it makes total sense. We know how you can take solar energy and turn it into electricity using the solar panel and all that stuff that goes on, the PN junctions, etc. We know the science behind that. It's not magic. It's all science. And this is all science too. It's just we haven't gotten our head wrapped around it yet. So scientists, get off your duff and stop being wimps. Stop worrying about what your academic partners are going to think about you if you start visiting PESN. We've got some great stuff. There's some great technologies, and this is one of many. There are 50 genres of clean energy technology, 25 exotic and 25 conventional: solar, wind, geothermal, tide, wave, ocean currents. You've got waste to energy, biomass. There are 25 conventional technologies. There are 25 unconventional ones, like this one. Cold fusion, zero-point energy, magnet motors, gravity motors. And they all have claims to working prototypes. Not just one, but several different groups on each one of those 25. So stop being wimps, wake up, put on strength, and let's be the God-endowed people that we were born to be. And stop playing into the beast and listening to what they have to say and following their tunes and poo-pooing science, calling this stuff junk science, when the tokamak reactor, that's junk science. How many billions of dollars have they dumped into that, and they still haven't even reached, they just barely this year reached Overunity for the first time, and they've been at it, 20 years? And they're supposed to be commercial and practical in 15 years from now. Billions of dollars, and we've got these cold fusion processes. They've not even spent $1 million on this. Just imagine what could happen if you put some money behind this and put some science and get some support behind this. Stop supporting the corrupt powers that be and support the new world that's coming. Thank you. That's one factor. Another factor is that well, I'm getting ahead of myself. I wanted to mention that when they put the anemometer, they had an opening that was about, I just got a syringe here to approximate the size. This is about 3/8 of an inch, and they had about a 1/2 inch opening when they were taking the hydrogen gas sample off to send to a third-party group for testing, for qualitative analysis of what percentage of hydrogen, oxygen, and other contents of that gas. As you blow through this, that sound actually approximates the 1,000 liters a minute. It's actually 720 liters a minute, because your lungs are about 6 liters. The average male lung is 6 liters. So if you inhale all the way and then blow out as fast as you can, which is about 1/2 of a second, just try it, time yourself. I did this on the plane coming back. It takes about 1/2 a second to vacate your lungs. And now with this is going to be restricting the flow, so it's going to be a little bit harder. But here's what it's going to sound like for 1,000 liters a minute. Well, actually 720 liters a minute of gas coming. This is air, not hydrogen gas. And so I'm going to inhale all the way and then blow it out. I mean, part of that noise was coming from the squeaking sound of my lips going around this thing. But let me just do that one more time. I mean, that's you can hear that, and that's fairly loud. The volume on the camera doesn't really do justice to loud or soft decibels, because it adjusts for the sound input, so it doesn't overwhelm the audience. But you can something along the lines of 2,300 liters a minute of gas coming out. And what I saw was obviously hydrogen gas production, but it didn't seem to connect to me that it was producing that much gas. And I ran some numbers. They had an anemometer that 1-inch diameter opening with the handle, and you put the 1-inch opening. They had a 1-inch, maybe 1 1/4 inch size pipe coming from the tank that was making the hydrogen gas. And as he placed the anemometer on top of it, it wouldn't turn. And it has like a 186 cubic feet per minute lower end limit on the anemometer, which I think comes to, what was it, 200 and it's like 3,000 something liters a minute. It's way up there. So it would make sense that wouldn't spin, even if it was producing the amount of gas that they were claiming. I was expecting, just trying to think, what would 1,000 liters a minute look like, or 2,300 liters a minute on their higher setting. And I was kind of picturing that you would have pipes that would be screaming because of the exhaust of the gas. I was wrong in that assumption, because number one, hydrogen gas is 14 times less dense than air. And so when you have air coming from a pipe, you have a certain air volume sound, you have to reduce that by 7 times. And so, if I was doing that with hydrogen, it would sound like, you obviously can't hear that from there with that camera. And so hi, Sterling Allen here, PESN. I just got back from the Solar Hydrogen Trends demonstration of their Symphony 7 hydrogen producer that was tested in January by Air Kinetics Inc., which specializes in those kinds of measurements. And their numbers showed an overunity in one of the data sets of 577 times. So for, I think it was close to 700 watt input, they were getting 577 times that much energy out in the form of hydrogen, which has a kilowatt equivalent. And so that was a rate of about, what they supposedly measured or what they reported in their data was